This is the lecture for Class 10, and we'll be working with remote sensing and density surfaces this week. We'll be paying attention to raster development within ArcGIS specifically. So we'll be spending time with the raster model as opposed to the vector model this week. Let's take a look at Class 9 themes real quickly. So in Class 9 we were using the ArcGIS model builder to replicate working processes from the assignment, and we had basically three types of elements. We had inputs, tools, and outputs. We were connecting these through what's called a connector. It's sort of a diagramming line tool, and the text labels were very important for understanding where our inputs or how they're named, and also the naming of our outputs so we can find them if we need to. And the model build doesn't necessarily drop in your features into a active map window. It's going to usually just default them to your Scratch folder or to a default geodatabase. We talked about criteria in suitability, and the classic suitability for GIS is this kind of Boolean either or math. That's a very hard math. It's not going to be what's called a fuzzy math, which is a little bit more about ranking and about setting priorities in a scale. It's a little bit more subtle. In Boolean, we're making very hard decisions. It's either inside this thing or outside of that thing. And these can be spatial operators or logical operators, and we talked about the difference. Spatial are things that are definitely about distances, and logical queries or logical operators are usually made in an attribute table, and they're usually selections that are happening within attributes. We talked about the cell value as being really critical to suitability. So when we're doing suitability, we're less interested about the full map page or raster extent. Certainly that's important at the very end, but during the processing, what's really happening is that the GIS is going pixel by pixel by pixel and making a valuation across all our layers. And what's really critical about that is that each layer has to be the same cell size, and it has to be in the same coordinate system to allow the GIS to efficiently go from cell to cell between each one of the layers to derive our final value. And usually what we're looking for in the final value is a combination that we know that we're looking for. The GIS result, hopefully that pixel value will be there that we can go ahead and then select as being suitable or unsuitable. We use a raster calculator oftentimes to form equations between rasters. So again, we're treating the cell value of the rasters as opposed to the larger raster extent itself when we're doing this type of math. Our criteria this last week, we had a series of criteria, and the first one was slope. So we worked with a digital elevation model to derive slope. After slope, we did proximity to roads, so we needed to be close to a major road. Then we accessed markets. We needed to be close to a market so that those that are both serving the refugee camp but also within the refugee camp have some access to these markets. We talked about it being away from ERW or away from some unexploded or some dangerous feature in the geography. And we also wanted to be away from dense urban areas that already are fully developed. So we want to find parcels that would allow for the siting of a large operation like a refugee camp. And through all those criteria coming together, we were able to get suitable campsites. Okay, so this week we're going to talk about remote sensing, and up until this point in the course, we've really been dealing with the raster model in depth. That's where a lot of our processing has taken place, and that's kind of the bulk of the class has been geared towards the vector model. This week we're going to start talking about raster images and where we can get them and what's important about them. We're also going to be talking about a subset of a raster, which is a density surface. So we're going to have a part 1 and a part 2. So the part 1 is remote sensing, and we're going to describe what that is. So this here is an image of a class, or a class of features in the landscape, and it happens to be forest loss. And if you look very carefully, you can see a line in the lower right-hand corner that's kind of going across the map page there. And that actually is the course of a tornado a few years back in Alabama. So at this scale, from this remote sensed raster satellite-derived image, we're able to make out a feature in the geography that is very significant. And this is coming from a project called Global Forest Change. This is based on the years 2000 to 2012, I believe. And if we this is a global project, and it's done at the University of Maryland in collaboration with Google Map Engine or Google Earth Engine, and they've done the processing globally based on satellite imagery. So let's go to our forest and tornado example in Alabama that I just showed. Let's zoom into that area. And here we can see that that line right there, that's our loss in terms of the actual path of the tornado. So at this scale, within this satellite imagery, we can make out large swaths of change over time. We're not going to be able to make out a house or somebody's block per se, but we can certainly make out these larger features based on the resolution of this satellite imagery. So satellite images are very important to show change over time and show our geographies that we're occupying at very specific scales. And we're going to talk about scale as being an important component of rasters here in a few minutes. The term remote sensing, this image is from one of the Apollo mission to the moon, and here somebody's actually taking, one of the astronauts is taking a photograph of the Earth. And this is an example of a remote sensed image, and I'll describe remote sensing in just a second. So this is the Apollo 17 mission in 1972, and a photograph was taken about 45,000 kilometers from the Earth. And the term remote sensing, it can apply to many different ways that we actually image the Earth. And we've been doing it many different ways over history. So obviously the 1972 Apollo 17 image is historically very significant. But even before that, we would image the Earth from afar. This is a picture of the Civil War, and this is the Intrepid balloon that was utilized to help troops get a sense of the battlefield ahead of them, and they would send these balloons up and would be able to demarcate troops ahead. They could see over the landscape much better than just standing in the landscape and getting up on the hill. They could get much higher from the Earth and could sense out the troop locations ahead of them. We do this casually or on an ad hoc basis, I guess you could say, or unofficially these days through kites and balloons. We can get a balloon up in the air, and this is from a project called Public Lab, and it's a grassroots mapping kit, and we can see that there's some helium and there's a kite, and importantly there's a Canon camera. So, and they're saying that's about $45 on eBay. You can get one of these Canon cameras. And through this kit, you can put together a remote sensing camera that will allow you to take images of the Earth that then you can georeference and bring into a GIS or into Google Earth. We also use drones quite a bit now to get above the Earth and take images, and this is being utilized quite a bit in agriculture. And also is starting to be employed for humanitarian aid efforts and also emergency management scenarios. So anytime that we're getting away from the Earth and we're trying to sense it, that's usually referred to as remote sensing. This video shows satellites that are currently in orbit. This is a couple years old, so it's showing satellites that are in orbit probably less than they are right now. So there was 13,000 at the time that this video was put together, this animation. There's more now, and we can see just looking at this video how many there are. There's just way more than we might ever imagine. And what's important is they're at different orbits. They're not all in the same position. Some are low orbiting, some are high orbiting. The video here will pull out very far in just a second. We'll be able to see these high orbiting satellites that are very far away from the Earth, very much like the Apollo photograph. So we use these satellites to sense the surface of the Earth, and some purposes are for spying, other purposes are for imaging in the public domain. Various countries operate their own satellite systems, satellite programs. So there's lots of purposes that we have satellites in the air, in the environment, and we utilize that imagery that comes from those satellites in different ways. And usually the result is some type of image that we can process in a GIS, and we'll see that it comes in the form of this kind of stripping. So it's not just one picture, it's going to be many different pictures that come together to produce a composite image. And it's very important in looking at this imagery that we do see that's kind of tile-based. And we can also see this if we go to Google Earth and we zoom in close to the imagery. We'll oftentimes see these little breaks between one image and another image where it's obvious that the sensing has stopped along the edge and we're getting into a new tile or a new scene. So here we can see that there's an edge towards the bottom here where one scene has a cloud and the next scene has nothing. And sometimes they'll be slightly, it's a slightly different position in terms of features in the landscape. So here we can see this road's a little bit off kilter right here. In addition to using satellite imagery and having the tiles, I'll go back to this image right here where we see this stripping of tiles. We oftentimes do what's called a flyover, an aerial flyover, and the resulting imagery will come to us. It comes from a plane, and the plane has a camera mount on the bottom, and the final information will come to us oftentimes publicly available through, say, a county in what's called an orthophoto grid. And orthophotos are basically photos from a camera mounted on a plane, and it comes from what's called a flyover. And the resulting imagery will come in this quad, so you can get to the imagery through orientation, the quad grid. And again, this is oftentimes publicly available at, say, a county or a state level for a GIS department. And this is very valuable for understanding a geography with a lot of spatial resolution, where we really want to see buildings and see, say, cul-de-sacs or components of roads, where knowing where the features in the landscape at a very high resolution is important. It's a little bit different than satellite images. So this term remote sensing, this is a process of acquiring information about the Earth's surface from a distance. and we're not physically coming into contact with it. So that's the kind of catch-all remote sensing at large, is just we're trying to learn something about the surface of the Earth from a distance. So it can be many different sensors and cameras, and we're going to talk about some of those in a second, and it can be positioned in many different ways. So we talked about the Apollo 17 mission being one photograph from the moon, reconnaissance balloons from the Civil War, where we're trying to see ahead from a troop position to, say, an enemy. We talked about using balloons and drones and just different ways to get above the Earth's surface and sense out that surface. Usually what we'll do in terms of satellite imagery is that we'll mount, or I shouldn't say we will, the space agencies will, mount a camera, some type of sensor on the satellite itself, and really what it's sensing out is the reflectance of objects on the Earth. And what's important is that we need to think about it less of being a camera in the traditional sense and more of a sensor that can sense energy. So each feature on the Earth's surface emits a certain wavelength. So fires and buildings and forested areas, they all have their own signature of this electromagnetic spectrum that can be read by these sensors that are in the satellite. And we oftentimes will send the information to what's called a band, and we can see at the top right corner of this diagram here, this is a multispectral remote sensed band here. So it's 1, 2, 3, 4, and the energy that's coming into the sensor is broken into these different bands, and that becomes very important a little bit later on in our lab, where we're going to be working with a product called Landsat. We think of it less as being just a picture like the one taken during the Apollo 17 mission of Earth, and more as a sophisticated product that is multi-banded, that has several layers of information in it. We're going to talk about the resolution of imagery that is remotely sensed, and there's 4 types: spatial, spectral, temporal, and radiometric. And these 4 classifications or categories of imagery, they're important to consider when we're evaluating what's the best satellite product to use for whatever purpose of mapping we're interested in conducting. So let's talk about spatial first, what that's all about. So spatial resolution is the pixel size as represented to the Earth's surface. So this is kind of the ground size of the pixel. And we can think of it in terms of a high versus a low. So a high resolution spatial image is going to have very small cell sizes relative to a low spatial resolution. And that cell size is going to be able to capture a certain distance on the Earth. So we can think of it in terms of a house. So if we have a 30-meter pixel size, which is a pretty good resolution imagery, we can see the whole house. And the resulting pixel output is just going to kind of fill the whole frame of that one pixel. If we have a 5-meter resolution image, which is higher resolution than 30 meters, we're going to be able to see different components of the house. So it's not only just the house, but actually certain segments of the house. And then at a 1-meter resolution, we're going to be able to see the whole house in detail. We'll be able to see the roof materials that are used, maybe if there's a deck in the back of the house, maybe a porch in the front. So we're going to be able to, at the 1 meter, which is very high resolution, be able to really make out the features on the ground. And we can see that the cell size is changing as we go along from 30 to 5 to 1 meter. So we're going from a relatively low resolution to a higher resolution. We can think about this notion of spatial resolution in terms of a football field. So Usually the Landsat that we'll use is a 30-meter product oftentimes, and we can see it at 30 meters, the Landsat 7 at 30 meters, we can capture kind of, let's say about a quarter of a football field. So we could take 4 Landsat cells and get close to the full football field. Now, if we were using a QuickBird, which is a higher resolution satellite product, that's going to be what's called a submeter. So we're at 60 centimeters at that point in time. That's going to allow us to see actually people in the stands. We can see this little red dot here. So its resolution, its ability to capture features on the ground is much more resolute. The trade-off there is that the file, the size of the file for the QuickBird file, satellite image file, is going to be much larger. So we're constantly trading off file size with the spatial resolution. Also, when we're dealing with a very high spatial resolution, a sub-meter resolution, that oftentimes is going to not be free. It's going to be something that we're going to have to pay for. Landsat at 30 meters is a publicly available product. So as we get to a higher resolution, the expense for the sensor becomes more. Let's just take a look at 3 common products, 3 satellite programs that are very common. The first one is MODIS, and that's 250 meter resolution. And we can see at that resolution we can kind of make out large areas of geography. We can make out, say, a large river perhaps. We can make out valleys, but we can't necessarily make out distinct separation of small parts of a city versus a non-urban area. Whereas in Landsat 7 at 30 meters, we can definitely make out at that level the difference between urban and non-urban. We can see major roads, and we can see certain segments of the city. And we can also see very faintly this little bridge that's connecting these 2 peninsulas right here. Now, in the Iconos, at 1 meter resolution, we can make out the actual bridge itself. We can make out very specific features in the geography, so we can see buildings. We can maybe even see cars. And then, of course, if we go to sub-meter resolution, that's where we might be able to even see people at that point. So once again, spatial resolution is all about the pixel size relative to the ground size, and how much we can sense out in terms of the image, in terms of the features on the ground. We also talk about spectral resolution. This is the second component of our remote sensed imagery. And spectral resolution is all about the size and number of the segments along an electromagnetic spectrum that can be sensed. And so that's kind of a mouthful there. What's happening is that energy in the Earth's atmosphere and on the Earth's surface can be measured in terms of electromagnetic spectrum, and our eyes can see one part of that spectrum, which is the visible color, the red, green, blue component of the spectrum. But of course we have radio waves, we have infrared waves, we have all this other energy that we may or may not be able to sense out with our own eyes. But what's important is that a lot of sensors in satellites can sense out many different components of that electromagnetic spectrum. And different features on the ground cover, excuse me, will have different reflective rates or different wavelengths. So vegetation has a different signature than does soil, than does the tops of buildings, fire versus water. All these features on the landscape, they have these different wavelengths, and across the electromagnetic spectrum we can sense out those wavelengths. So we can see visible, but a satellite can gauge all the way from, say, gamma rays down to microwaves, infrared. So the classic component that the Landsat program captures is it does very well with visible and infrared. Some of the other components of the electromagnetic spectrum it might not do so well. So when we talk about the spatial or the spectral resolution, we're really saying what's the satellite good at picking up on this whole array of energy. What's it good at doing? And some satellites are better at certain components of the spectrum than other ones are. And again, what we're trying to do is we're trying to gauge the features on the surface of the Earth in terms of their signature of these wavelengths. So here on the bottom we can see that vegetation is very high at near infrared. Okay, and soil has a signature that's lower, and at the visible range we can make out water versus land. Okay, so there's different wavelengths by which these features are measured, and satellites can pick up those particular wavelengths. We also talk about the temporal resolution of imagery. This is the amount of time that passes between collection periods. So in the case of Landsat, which we're going to be dealing with, Landsat is collected every 2 weeks. So every time we want to get a new scene of Landsat, we need to go 2 weeks ahead or 2 weeks back in the archive. And the way that satellites work is they are on an orbit. It's usually a polar orbit, and the Earth's rotation is also moving too. So as the Earth rotates and the satellite moves orbiting around the Earth, we're getting different positions. And it keeps doing that over and over and over again until it gets back to its same position that it was in Landsat's case 2 weeks ago. This is a quick little video of Landsat moving. So let's kind of take a look at the actual satellite moving. So here in the key insert map off to the right, we can see the red dot. And the red dot's right at the border of Canada and the United States. And as it comes over the top, we can see these towns and cities ticking by. So it's moving much quicker than an airplane moves. And as it's going along, it's picking up a band of information. So it's a very distinct area that it's picking up in terms of sensing geography. And it's a very formatted, predictable orbit by which it's traveling. And here it's coming across the border right now in our little key insert map there. There's different temporal resolutions to different satellites. So Landsat we can see is 16-17 days there. The lower orbiting weather satellites are oftentimes within a day. They'll be in the same position. Then we have the spot satellite product, which is about a 30-day product. And then we have aerial photographs. These are the flyovers that oftentimes happen with airplanes. In a county or a state GIS program will oftentimes do those at, say, 5 or 10-year intervals. So those are very expensive endeavors to actually get the plane up, get all the imagery taken, and that's usually called a flyover, and that happens, its temporal resolution is very low because it's so expensive to do that. We also talk about radiometric resolution. This is the last of our 4 resolutions. So with radiometric resolution, we're really talking about the brightness of the image, and we store that brightness in terms of bits. And what we're really trying to capture is how many values can we see in the resulting imagery. So if it's a Boolean, just 2-color image, that's going to be a very low radiometric resolution. So let's take a look at 4 examples here. So here, under 2 values, which would be 1 bit, this would be like a Boolean result. Our radiometric resolution is very low. Whereas up here with 16 bits, we're a little bit better off. So here we can see all the colors in a rooftop or all the colors across the forest area that has many different shades of green. So its resolution, its radiometric resolution is much higher than just a simple Boolean yes-no type image. So we need to think about the resolution sometimes when we're trying to really sense the difference in a certain category of land cover. We often store our different bits of information in 3 different colors, red, green, and blue. And we bring those 3 bands or 3 layers together to oftentimes get a final image or a true color image oftentimes. And what's important to realize is that that the values, they can be stored in a multi-band product across different bands, and then the final result we need to usually compile in a GIS to get the full array of values available to us. And we'll do that in the lab this week, where we actually bring together bands of red, green, and blue to give us a final image value. Let's talk about the Landsat program. So the Landsat program we're going to be utilizing this week in class. It's going to be something that we can access in an open data format, which is interesting in and of itself and very easy to work with in a GIS. So let's watch this video for a second.
Their orbit goes from pole to pole and they capture a new place. And then every 16 days they start to repeat that. And it's been doing so for 40 years now, continuously orbiting, collecting data.
NASA takes the lead on the development of all of the space hardware. They build satellites and they put them in orbit. Once they're in orbit, we collect and distribute the imagery and ensure that the data are preserved over the long term.
Working with satellite data is important because we can monitor the environment and how it changes over time in a very consistent way. We can quantify the dynamics, whether it's related to agriculture expansion, fire regimes, deforestation, urbanization, and have a record that allows us to relate those dynamics to the drivers, population or economic policy, and what have you.
It's really kind of an underpinning of what we need to know to understand the health of the planet.
One of the really big stories of environmental change is the deforestation in the Amazon. This whole area here, if you go back to 1999, the vast majority of it is intact forest. And you can just see the herringbone roads come out through the forest, and then roads come out from those, and the land clearing and the forest disappearing.
The value of Landsat is in the use of the data. That means that the data have to be in the...
Okay, I'm going to pause it there. So the Landsat program, just based on this little preview video here, is pretty powerful in terms of a product. And what's really important about it is that it's been running for nearly 40 years now. So we can go back in time and we can look at imagery and compare it to imagery that's much more recent and see change over time. So with Landsat, we talk about it being a multispectral product, and what that means is that it's composed and delivered in multiple band formats. So the satellite sensor on the Landsat satellites captures the radiometric spectrum across different bands of information, and what's provided to us is those bands in a separated format. So this upcoming week we're going to be taking the bands themselves and combining them in different ways to create different scenes. And we can think of this literally as different rasters within the full raster set. And we can see here we have band 1 through band 8. And band 1 is collecting visible blue, Band 2 is visible green. Band 3 is visible red. Number 4 is near infrared. Number 5 is middle infrared, and on and on. So this is really great because we can separate out these bands and use them independent of each other in different combinations to get to the final result that we want to achieve. And in ArcGIS, what we'll do is we'll bring these in as single band raster data sets. We'll composite them, and then that's going to give us the multi-band raster data set that then we can view in a red, green, blue composite. Okay, so we can actually see the final results of our different band combinations as one final image. But we have to have the GIS actually do that band compositing. That's not something that we can do outside of GIS, really. There's different ways to do that, but it's going to require composing those bands with some type of software or some type of programming. So Landsat applications. So what do we use this particular satellite imagery for? We use it for land cover classification, land cover change. It's very good for irrigation issues and wildlife issues. It's very good at showing burn severity and also rangeland management. So anything that's happening at sort of a 30-meter resolution, that works out quite well. If we're trying to map the change of a particular house, this is not going to be the satellite product for us because its spatial resolution is set to essentially 30 meters. So anything less than 30 meters is going to be very challenging for the sensor to sense. But anything greater than 30 meters, it does quite well at. We also talk about classifying the images that come to us. So once we have our imagery in a composite, which we'll do this week in the lab and also as an assignment, we need to classify the image oftentimes to do it either as supervised or unsupervised. And basically what we're doing is we're looking at the imagery that comes to us in the multiband format, and we're basically trying to figure out what are the different features in that resulting imagery. What's the urban area versus the non-urban area? What's the water versus actual land? What's one type of tree cover versus another type of tree cover? And to do that, we need to basically classify the image. So that's kind of a next step with any satellite product, but specifically Landsat imagery. And there's two ways that we do this. We supervise ourselves, so we're the ones who's in charge, and we create what's called a training set or a training session, and then we classify the image. Or we can let the computer do it. And when we let the computer do it, it's going to use a clustering algorithm to find clusters in the image and then assign a class to that. So if it sees a bunch of pixels that are of a certain value, it's going to assume that all those pixels are very similar in terms of what they are, and it's going to assign it a value. So for all the values that it sees that are kind of urban, that have sort of a reflective color that looks like urban, it'll assign a number to urban. And then for trees that are real deep and green, it's going to assign another class for trees. For water, it's going to do another class. So that's kind of letting the computer do its own thing in an unsupervised session. And you don't have as much control over that, but what's nice about it is that it's relatively quick and easy to do. Whereas when you're doing it yourself, supervised, you have to really think about the imagery and what you're trying to class. And usually we'll start out with the multi-band product in GIS. Say on the right-hand side here, we can see it's kind of a true color image. And we can see what looks like fields, agricultural fields, then some forest area, and then it looks like a water body here. And with a classed image, we can see that we have water. And then this yellow color looks like they're calling it rain-fed. And then our light greens and dark greens. These are all mixed and broadleafed and needle-leaf forests. Okay, so our croplands, we can see those down in the bottom here, and in our class products it's also calling those rain-fed or maybe a grassland. So we really want to get to the classified imagery because that's really telling us more about the features. We're classifying the features in the satellite imagery, and what's important once you get to a classification is you can compare classes over time. So we can see how a flood takes place in terms of the growth of that particular water class, or we can see how urban space is subsuming non-urban in terms of a growing city. We can see how crops might be overtaking a previously forested area through change over time. So classing an image is very important in addition to just doing the bands, to compositing our images in a band format. We'll oftentimes give names to these classes. So this is kind of a classic land cover classification. So water versus urban, barren land versus cropland, wetlands versus tropical mixed forests, snow and ice versus a forest itself. So we want to know the difference in terms of land cover. We want to know where certain features are because we want to be able to measure those features. And what's really important is that in the raster itself, it's the values behind each raster cell that is really critical, because once we have a number, then we can associate that number with something that's much more qualitative in terms of, say, a forest type or an urban type, some type of rock formation. So we can start talking about those numbers in terms of qualitative classes. We oftentimes use Landsat for change detection. So we can see, in this case, we're looking at Mount St. Helens in 1975 versus 2000. And we can see that massive change due to that volcanic eruption that took place at Mount St. Helens. We can see the vegetation decrease. So we can make out certain features in the satellite imagery that we're interested in. Oftentimes we are interested in vegetation increases and decreases, and Landsat does a pretty good job of capturing that particular classification category. So we can use Landsat imagery to show the change between different years, 1975 to 2000. We could also do a different year. Let's go 1990 to 2000. So 1990 to 2000, we see that the volcano already has happened, and we can see that the decrease is not so great. In fact, we can see some increase right around the river itself. So we can see a little bit of that vegetation that was lost coming back now in terms of that bright vegetation cover. Okay, so again, Landsat is really good at showing change over time at a very specific scale. So it's not going to show us an actual house being moved or being changed, but it will show us these larger landscape patterns. And we start off with the first top layer here, which is a banded product in GIS. So we look at the bands, and then we either supervise or unsupervise to get to our classification. So in the bottom here, we can see in 1973 we have a developed area that's classed as blue, and we can see it up here in the imagery. It's kind of this brighter color. It's kind of the reflectance color is almost white. That's what the classing sees as urban. And then we can see what happens all the way down here at 2000, that massive growth in terms of the red land category, which is in this case developed land. That's the one that's really growing. And in the first images, before they're classed, it's hard to make out that change over time. But when we class the image, boy, you really can see the difference in terms of your different classes, how they change over time. On the left-hand side here, this is a fracking pad, and fracking pads are many acres in size, and they are large enough to be noticed within Landsat imagery. So on the left-hand side, we see 1973, and we just see a few of those pads in black. In 2000, we can see that huge growth of those pads, and the Landsat imagery can pick up on something that size. Again, it can't pick up the actual items on the pad itself. It can't pick up the drill wells and the infrastructure on the pad, but it can sense out that there's a change in the landscape or change in the geography from the pad structure itself to what's right outside of it. So the yellow is this grassland, shrubland, and then the mining is this black color. Okay, so we'll be working with Landsat imagery this week, and we'll be exploring how we can manipulate it with GIS software. And what's important is that there is quite a bit of satellite imagery that's open and that's in the public domain now. And there is also really high resolution imagery that oftentimes, unfortunately, we still have to pay for, just because those satellites are so expensive to launch and maintain, and private companies are doing those. But we do have a lot of public domain satellites that are available, and Landsat being one of the biggest and most important programs. The second thing we're going to be doing this week, or at least talking about, you may want to use this for a final project. We're not going to go in depth with it for the actual assignment this week, as we're talking about density surfaces. And density surfaces are basically points data. So we're deriving the raster differently than we are from a satellite image. So they don't have anything to do with satellite images, but they are very much about a raster result. Okay, so they're a cell-based result. And I'm going to use this example here. It's called the geography of hate, and this was developed by a professor and research team at Humboldt University, and what they're looking at here is tweets, actual Twitter tweets, and they're taking the geographic information of the tweet itself, and about anywhere from 10 to 20% of tweets have a latitude and longitude. They're turning that data into an actual point, a vector point of latitude and longitude, and then they're sending it to a density surface. So where there's a lot of points, where there's a lot of activity in the geography for a certain category of tweet, they're making a raster, a hot zone, what they're calling more hate versus less hate. And they have different categories, so I'll click on disability. So they're looking for the word cripple in their methodology, and we can see that pattern is completely different. And there's these certain hot spots where that particular word is used in tweeting for whatever reason. And what's important about these density rasters is that we can see the larger pattern in a points data set. So it's really a visualization tool to show relative density between high and low. We oftentimes see this kind of pattern in weather satellites, or not weather satellites, I should say, in weather radar. And what's really important here is that the actual measurement is taking place through radar. It's not actually taking place through points, but the patterning is very much similar to density surfaces. And you have this kind of clustering affair that's oftentimes ranked very high, and then as you're going outwards in terms of the density, it has this kind of what's called a kernel shape to it. And the kernel shape is kind of the shape usually of density across the continuous surface. So you'll see kernels showing up on a repeated basis. And this week when we do our in-class lab, we'll be looking at kernel density as a process that we can do to develop density surfaces. And it's based on the notion of interpolation, or averaging across the space. So we're taking inputs into our GIS, and then we're kind of averaging out across the surface the results, and we're finding these pockets or these kernels of density. We can also think of this in terms of, let's use the example of street trees in Manhattan. So there's many different street trees, and we can see kind of the overall pattern in terms of their actual points location. So we can see some clumping, but we really can't make out the visual pattern of the highs and the lows in terms of density until we go to a density surface. And it's important to realize that as we go to a density surface from the original lat-long points, we're giving up the specific lat-long location for a relative high versus low density. So those areas where we see a lot of trees that are kind of clumped together, those are going to give us the high density locations, that top green color. And the areas where there's just a few points, those are going to be our low density areas. So we can also use density surfaces for many different purposes. And one of the purposes that it's utilized in humanitarian work is to gauge proximate population in refugee camp management. So what can happen here is that a point can be placed on a tent structure, which is semi-permanent, and actual population can be given to the point. So some camps, let's just as an example say that one tent is worth 20 people, or 20 people could occupy one of these tents. We would say that the population per point is going to be about 20. And then in those areas where we have a lot of tents clumped up together, obviously the population in that area is going to be higher. So here we can see our high purple per hectare is 660 and a low would be 1. So on these edges of the camp, obviously there's not many people, but for whatever reason, there's a lot of people right here towards the top of the camp, in the middle of the camp. And this is really helpful in management of spaces like refugee camps, where population density becomes really critical towards the larger management of the structure itself. The way that density surfaces work is they're based on the notion of observation in one place. So we're going to be in the middle of a cell across our raster surface. So there's many cells across the raster surface, and at the center of each one of those cells, we're going to have a certain amount of features that we collect. So at this particular cell in this fictitious diagram raster, we're collecting 1, 2, 3, 4, 5, 6, 7 events out of the full array. And then we can get observations per search area size just by dividing it by this search area radius. Okay, so it's the full search area radius, it's its relationship to the number of observations. So if we go down here a little ways to another center of a raster cell, we're going to collect a whole different array, a number of observations, and that's going to give us a different number. So once we have all these numbers within our final raster, then we can calculate the relative density from cell to cell, and that's kind of how we do this. We have a points feature, a lat-long points feature usually, that then is going to go to a raster layer. And what's really critical is the actual search radius going from cell to cell. So in this case, we can see that our resulting cell rank is going to be kind of low. It's 0 to 3.2 here because it's only capturing 3 events within that search radius right there. Now we go to the one over on the right hand side here, and we can see the search radius has remained exactly the same, and it's gone to another pixel, the center of an adjacent pixel, and now it's picked up 1, 2, 3, 4, 5 events, and it's going to class that down here in the 3.2 to 6.3 range. So it's giving more weight to the raster center that collects more events, more lat-long events. And here, once again, it's 3, and then here it's 1, 2, 3, 4, 5 events. And we can see that the location of the events hasn't changed. The only thing that's changed is the search radius at the different cells. So it's going through the cell arrangement within the raster, and it's counting up how many events are taking place at the center of each cell, and that's how we get our relative density raster. So how do we determine a search radius? We can use the GIS to suggest a search radius to us, but we can also think about it in terms of large scale versus small scale mapping. So in this case, we would want to have a search radius that would be able to pick up these events, and I'm assuming that this distance between, say, these two guys walking here, these two lat-long events, is probably about maybe a half a mile or so. And so I don't want my search radius to be much more than that. So on average, my events are about this distance. So a half mile to a mile search radius would make sense for this particular data set that I have here just for Manhattan in terms of pedestrian or bicycle use. Whereas if we go to a much more smaller scale mapping of all the United States, and I wanted to map, say, the density of cities, I would want to use a search radius that would be much larger, because I would want to be picking up these clusters of cities. So I might take the difference between Jacksonville and Daytona Beach, what that straight line distance is my search radius for the full density surface raster. So again, I would be going from just a half a mile to a mile or a quarter of a mile in this data set to probably many miles, maybe hundreds of miles, so it would be more appropriate to the scale of my mapping. So again, the GIS will oftentimes suggest to you the correct search radius, or it will just default and run a default, but you can change that search radius size depending on the scale at which you're mapping and the clustering of the events. How far away is each event away? On average, is each event away from the other one in your surface? That's the end of Class 10 remote sensing, and hopefully this gives a nice introduction to satellite imagery and how we can work with it in GIS. And Landsat is a very important product that we'll utilize this week. And also density surfaces. Oftentimes we'll have points features, lat-long points features, and they could be, say, from a survey, or they could be from a GPS data set. And we want to figure out what's the concentration of our points. Where's the highs and the lows in terms of different concentrations? So good luck this week.